did a review of all the soil sort of geology and geotechnics of Dublin in 1990, the paper, and I had access to the Dublin Corporation. At that time things were a bit different, things weren't online, and I compiled together a lot of geotechnical information for use for geotechnical engineers and structural engineers and everyone else. And also at that time I sort of gave a state of the art of what the current practice was and what the understanding of the properties of the various soils were at that time. Now what I hope to do now is just go on from that. Now, I know you don't have the 1990, but I'll give you a background to where everything was at that time and see what we've learned in the major construction boom that happened during the 1990s and 2000s up to today. So I want to draw on that experience. I want to introduce the particular geological features of Dublin. If you're going to do structural design in Dublin, you should know what you need, where you're putting your structures and where the soil, where the geology and geotechnics change throughout the city. Initially I had intended to relate everything to the Eurocode, which also came in this period, but I don't think I'll be able to do that because of the time constraints. You'll be here all night if I start bringing that in, but I will make some reference to Eurocode and to where that comes in into the design. And then I want to go on then to present some design and construction issues in relation to foundation bearing pressures, pile behaviour in stiff black boulder clay, calc limestone, highly weathered granite. I'll also review some of the information on retaining wall performances, and I'll also talk about the port clay, which is in the harbour area of Dublin. So what I would class as the particular geological geotechnical features in Dublin is, one is a pre-glacial channel that runs through the centre of Dublin, not along the Liffey but offset from the Liffey, and I'll show you that in a moment. We also have the broad black boulder clay where we're putting the foundations on. That is ubiquitous over much of the city, and I just summarise what we understand about the properties of that clay. We have a major east-west fault that separates the solid geology, what I would call the limestones, from the granite. So if you're south of that fault, you're in the granite. If you're north of that fault, you're in limestones, and your ground conditions change. You also, in this time since 1990, pyrite has become a problem. So I'll briefly discuss that because pyrite is really a problem for reusing materials. It hasn't been to the same extent in relation to foundation pressures. The port clay, I'll introduce that, and there are sundry other ground conditions around the city, made ground, alluvial, estuarine, which I won't go into and really have to be treated on a local basis. I always find it interesting that when we are going to look at the soils of Dublin, that you have to understand what has gone on in the recent past, and in particular in relation to the water level. At the end of the last ice age, which was about 10,000 years ago, something like that, the water level out in the Irish Sea was about 30 to 40 metres lower than it is now. So consequently, river channels, erosion features eroded to that datum, not to the ordnance datum that we have now, and obviously that affected the channels that were cut in to the rock. Apart from the fact that the glaciation cleaned up much of weathered rock surface and left us with the strong rock. And then you see then that about 5,000 years ago, the water level is actually higher than it is now. And it's now coming back down to, well, it's now where we think is normal, whatever normal is. As we know, that's going to change in the future. Now, this is the pre-glacial channel. Now, the pre-glacial channel is there. That's the channel there, and it goes down to 40 to 50 metres in around the Rings End area. But it does come up, and it goes up through Fairview and to a certain extent up around O'Connell Street and areas like that. And you can see the current channel of the Liffey there. So it does go in. That is going down 40 or 50 metres. Obviously has been filled in the time, and what's of interest to us is what is filled in with. Now, so around here we would have our typical boulder clay over bedrock, 6 to 10 meters sort of thing, that sort of area. But we can see, we can expect different geological and geotechnical conditions in that zone. This is O'Connell Street. You can see this, this is courtesy of T.J. O'Connor's is Dublin Central, one of the major projects that sort of supported. The sort of ground conditions you get there. And this is the ground conditions that's relevant to the metro. There's a metro station there. In fact, we were involved in some of there's one metro station is half constructed at the moment in anticipation of something happening. So you can see there you've got sandy gravels and boulder clays, and here in the O'Connell Street area, and the rock goes down much deeper. And you have other issues, like one of the issues is identifying boulder clay and sands and gravels from the rock, and it can be quite difficult in places, and it is relevant to founding levels for piles and constructing piles and everything else like that. So that is sort of conditions that have been infilled into that sort of materials have been infilled into the glacial channel. And then in the port area here, you have the port clay, which has a tricky, I'll go on to later on, but it is a clay. It's not a boulder clay. It was a lay down, what we call lacustrine, lay down in lake conditions, and significantly its strength is of major significance. When was it laid down? Is it soft? Is it firm? Is it stiff? What are the stiffness properties? And also it contains, it's laminated in areas, and sand layers do cause an issue with it. Just to give you an idea of where you are, thickness of it, you can see that's greater than 15 meters thickness. The port clay, these are projects we have been involved in, or we know information from. You can see there it's more than 15 meters thick. There it's more than 15 meters thick. There. Now it doesn't mean that it's not more than 15 meters thick here. It's just that we don't have information on it to infill that. And then you had at the end of it, the Dublin Port Tunnel. There is a paper produced on Dublin Port Tunnel, which they did encounter some estuarine material, which is different to a certain extent than what is there, would appear. But that is just a detail that we needn't get involved in. So that is another soil that is particular to Dublin that you have to take account of, and I'll come back to it later on. The other thing is that we've got this fault here. You see, we've got granite this side of the fault, limestone there, and we've got granite on this side. So the fault divides the city. If you're north of that fault, you obviously have a different ground conditions. And then in the granite, if you go down to Sandyford area, where AGL is, the granite is the rock picker trying to break granite can be heard throughout any development. But granite has its own features, which I'll talk about. It's not all hard, and that can cause engineering problems. This is a sort of historic map that I generated years ago, or at least I got a copy of it from someone, but it had never been published, and I often wish I think it should be, because this is just a hand coloration that I did many years ago. But it does show some of the the variation in soils that you get. Now, the first thing is that I put this up to let you know the Geological Survey of Ireland has a very good online website. So these sort of maps, coloured maps now, can be useful as an indication of the sort of ground conditions that you might expect. But you can go online with the Geological Survey, and they have a lot of this stuff in digital format, and you can overlay on your own maps and so on. And also what the Geological Survey have is they have a database, and you can go on and find out boreholes on any site that you you're thinking of developing in Dublin, go on to Geological Survey. They'll show you, you can pick out the boreholes, and you can go online and see what the boreholes found. It's not the best, not as much detail, but it's very, very useful if you are proposing to develop in Dublin. So the sort of thing that you'd look for from these detailed maps are the boulder clays. You see raised beaches, you get gravel beaches, Rings End and up there, because I told you the water level at one time was higher than now. And then, interesting, the old maps, and anyone working in Dublin it's essential that you look at historic maps and you look at old drift maps that were prepared before a lot of the made ground was placed around Dublin, because there's old quarries where you don't expect them. Like, I don't know, the big one I know is Fitzwilliam Square, the ESB building. That's built on the side of an old quarry. So one side the rock is about 3 meters down, and you go the other side of the building and it's down about 20 meters or something like that, because they've quarried out, it's on the side of a quarry. So these are very useful, and as I say, Geological Survey or the old maps will help you in that, finding your way around those. So it gives you a background to the geology and what to expect in Dublin. Now I want to go on to look at some of the properties of the material that we will deal with here on sort of a day-to-day basis. First of all, this is what we call a boulder clay. It's called, geotechnically we call a lodgement. They're all the same thing. The ice came, the sheet of ice came, and it ground the rock at the bottom between the ice and the rock. It ground the rock down to small pieces and large pieces. So we've got a mixture. That's the lodgement till that you see. And the unique feature of it is that it's made up of small particles that are as small as clay, up to silt, sands and gravels. There are some boulders in it, not enough. The term boulder clay is just a title given to it, but it doesn't always have boulders. But what it does have, what is well known, is that it's very dense, it's well graded, and consequently, because it's well graded, means that you've got sand and gravel particles, and the voids in those are filled in with clay. So you get a very low permeability material. So, and that has significant bearing on its engineering properties, and I'll talk to you about that later on. So this is the brown boulder clay, and that's the black. And then, interesting, the last talk I gave in 1990, at that time there was an argument between whether the brown boulder clay was a separate stratum from the black. But I did some work with P. Coxon from the Geological Department, and we did tests and everything else, looking at the striation and the order of stones, and it was obvious that the brown boulder clay is the weathered zone of the black. It's not a different stratum, and that has been confirmed by various studies for the Dublin Port tunnel and so on. So it's interesting. That gives us problems I'll tell you about later on, but it does give you sort of an idea of where all these materials come from. So the brown is the weathered portion of the black boulder clay, and the black is very stiff, and it is very low permeability, generally. In geotechnics, you can't get away without talking about groundwater, and then structural engineering, basements, anything below ground, obviously, you're talking about, it's important. I put up the slide there at the beginning there is in relation to O'Connell Street. Generally, around O'Connell Street, the gravel is less associated with the River Liffey. It's what we call a coastal aquifer. The water level in that is governed by mean tide level. So you'll find that anywhere O'Connell Street or in that coastal aquifer, that the water level will be around 0 metre OD, plus or minus half a metre or something else. You're curious enough, when you get down to the port, it rises a bit. It gets up to about plus the mean tide level. And that mean level, and I think I've often wondered, was that due to being the coastal aquifer next to a greater salt content in the material, but I never got a chance to research that. Now, this is an excavation. Do you see that big excavation here? It was a trial excavation, which I'll be talking about later on, was carried out as part of the Dublin Port Tunnel. They people came, they looked at it and they said, look, this is black boulder clay, it's as hard as the hobs of hell. It stands up. Why can't we let it? The section from Whitehall up, there's about a kilometre or a kilometre and a half, which is going to be cut and cover. So what they were going to essentially building concrete units in a trench. So the question is, did they have to support the sides of the trench? And it's down. That one is down 11 metres, and in some cases down 12 metres. So they say, why can we get away without any side support? Will it stand up long enough for us to build our structural units in the dry with just a little bit of pumping and without putting any secant walls or anything on the side of it? Now, the reason I'll be coming back to this later on, that was the trial that they carried out. But what I want you, obviously, you're seeing that it's a dry face. Everything was essentially dry, a little bit of weep. But there's a lot of work was done around the Dublin Port Tunnel by Mike Long from UCD, Chris McKeety from GCG in London, and various other people. But they measured, before this trial, they measured the water pressures in the ground. Just to show you that although that's dry, beforehand, it's black boulder clay, it's hard, but all the pores are interconnected. And essentially, the water pressure is hydrostatic once you get below the water table. There, the water table was about 2 metres below ground level. And below that, you may as well, the water pressure is the same as if you're in a swimming pool. It's just 9.81 times your depth below the water table. That was the water pressure. So it's the same as if you're in it. And so that's measured. Some people find it hard to believe that when it's dry, they think there's no water in the boulder clay. The boulder clays have about 30% porosity. And so 30% of the boulder clays are made up of water. It's just that they're very fine pores. And the only time you'll get anything partially saturated is in the upper zones. Okay, I'm just going to briefly mention design of Eurocode because it came in, but it's a subject that is too big to be included in this talk as well. But Eurocode has introduced things like derived values, derived parameters and characteristic parameters. Eurocode also brought in a greater requirement of geotechnical analysis in all our projects. In other words, now when we do a project, we would do what we call a GIR, that's a ground investigation report, which will summarize the findings and take them up to derived values from your ground investigation. And then you would do a geotechnical design report, which is your design, and that would, in the part of that would be determining your characteristic values from your derived values. Now, I won't go into it in too much detail, just to say here, a lot of it is when you're doing geotechnical design, you have to think of undrained strength parameters. That is before water has time to dissipate. Your drain parameters, ultimate limit state and serviceability limit state. Now I put in here MV and E dash. MV is from the value that historically people tend to get from to use from odometer tests. But a lot of the analyses now are done like assuming either elastic modulus can be linear or non-linear elastic modulus. That's a lot of the most of the analysis now. Even for a simple structure, if you're looking at a foundation, that's the sort of equation we typically use now for settlement of a foundation, where E dash is a derived is your elastic modulus. You can generally assume a linear elastic modulus. Q is your bearing pressure, B is your width of foundation, mu is just your Poisson's ratio, and IF is an influence factor based on the length and the width of your parameter of your base. So that's the type of settlement calculation which is used in many of the geotechnical design reports. But there is still room for a presumed bearing pressure. And that's really what I'm going to talk about tonight. Presumed bearing pressure is when you have a small structure and it's a small, simple structure, and you just want to look at it from sort of what was traditionally allowable bearing pressure. So it would be based on characteristic load values. And I will use that term more than anything, more than go into the more sophisticated geotechnical analysis. We have also issues with retaining wall and stand-up time in undrained conditions, which I'll come to later on in the presentation. So nothing much about Eurocode. Essentially, what I'm saying is I'll talk about presumed going back into old money rather than into the new Eurocode terminology. Okay, now I just want to say a few words now about foundation design in the soils we have around Dublin. I told you a lot of our foundations are taken into the brown boulder clay, and we need to know how to get the strength and stiffness parameters of the brown boulder clay, and you do a ground investigation. Much of our values are got from ordinary SPTs. That's I presume you know what an SPT is, from a ground investigation test. It's a crude test. There's a lot of things that are wrong with it, but it is still the most used parameter in boulder clays for routine design. You can take, and you may like to think that it'd be better if we took a so-called undisturbed sample. There's U100s and there's so on of your sample and test them. But experience and in situ testing has shown that the values you get from laboratory tests and samples taken with U100s, be they consolidation tests or strength tests, underestimate underestimate the performance of the boulder clay. In other words, it'll behave much better than you would think based on laboratory tests generally, unless you do sophisticated laboratory tests and bring them back. That's all because the sampling process just disturbs it too much. And so the problem is that if you get a test result and someone has to make a judgment of discarding it or not, but generally you will find that if you use settlement parameters from those, you'll find that everything will settle far too much. These are the techniques, these are the relationships we use. The undrained shear strength is 5 to 6 times NSPT KPA, and then E dash, that value of elastic modulus that I told you about in the settlement equation, and it's 1500 to 2000 times SPT. So in routine design, that's what we'll be using nowadays. If stiff, then presumed bearing pressure. Now in the brown boulder clay, the presumed bearing pressure is generally, if it's stiff, you use 200 kPa. Now the fines content has particularly important. It's okay if everything is stiff, but if the thing isn't stiff, you have to find some way of justifying a foundation bearing pressure, and that can be difficult. I come across this on certain projects. Like the only time that someone would ask me to look at something is when they have a problem, because if it's ordinary routine, they just do it themselves. And very often you're going in and you've got a brown boulder clay and they do a trial pit and it looks soft, and yet the costs of going down to under they could be significant, so they need some sort of judgment, some sort of test to find out what this in situ performance is. And it's not easy. In some cases it's easy, you can use the SPT, but in various SPTs sometimes get it wrong. There's the probe, the dynamic probe that's around now for continuous, and even with those, some of the boulder clays behave strangely, and it's usually around this thing that I'm going to talk about later on, is the percentage of fines in the boulder clays, and that has a significant effect on the performance of it. So I just show you an idea. I've been trying for years to get the ideal method of getting all the properties of these boulder clays. I've tried CPTU, I've tried the Marchetti dilatometer, which is a spade that you put in, which is the hot thing in some parts of Europe. I've tried pressure meter testing, and we've tried seismic methods. But the dilatometer, pressure meter, and the CPTU didn't work because the stone content was too large. The pressure meter test, curious enough, just the insulation effects were quite significant. The seismic method may have their uses. It is being used more and more in these days, but it's not perfect either. So anyway, with the brown boulder clay, as I say, routine SPTs, if you are on a marginal material, it's difficult to get an ideal way to find out the properties for design. Now we're going on to the black. This is the unweathered part of the lodgement hill. A lot of work has been done on this in the recent years, brought on by the Dublin Port Tunnel, by projects like the Dublin Central that I showed you before, where there's a lot of bucks around. They have to have fairly confidence that they are getting their of a design. And typically, so there is a way of getting good samples of the black boulder clay. It's a rotary drilling technique. It's not you don't hammer something into the ground, you drill it, and you drill it under certain conditions. But if you have SPTs, it's still 5 or 6 times an SPT, and the E- is still 1500, 2000 NSPT. If very stiff, then the presumed bearing pressure is about 400 kPa. It was like that in 1990. It hasn't changed since then. A lot of in situ tests have been done. This is a foundation test that I did that was presented years ago, and the results of that are still used, and it confirmed the stiffness of black boulder clay and that you can put a big bearing pressure on it. Talk about the strength of the boulder clay. Probably I just want to get this out. It doesn't go. Okay, we talk about the undrained shear strength in the same way you talk about it's not the unconfined compressed stress of concrete. It's actually the undrained shear strength is shear. It's about half your the strength, compressive strength of a concrete, because there's a shear stress. And put it this way, the sort of values when you measure the undrained shear strength on good quality samples, these are consolidated samples have been consolidated, you find that the strength of the black boulder clay is around 450 to 500 kPa. Now, to put that in language, a weak rock would have the black boulder clay we have here could also be called a weak rock based on strength, because that's the sort of strength that a rock would have. Now, if you want to do advanced design, you can use parameters which you'll come on to later on that. Now, I'm just going to put in this slide really in limestone because pyrite is a big thing. The bearing capacity assessment on limestone is usually done on EC7 has a method of determining presumed bearing pressure based on the strength of the rock and the condition of the rock. I just put this in pyrite assessment based on local conditions, but generally, if there is an issue with pyrite, the rock is blinded immediately on exposure where significant pyrite is suspected, and that's in relation to foundations. There's another issue, of course, if you're using limestone as fill material, but that's not what I'm talking about here. The stand-up time for excavations in brown and black boulder clay, because this is something that you're all dealing with. If you're going to do a basement, ideally you want to do it for minimum cost, and so if you're doing a retaining structure, concrete retaining wall inside, you don't want to have to put in side supports. So what is the stand-up time for excavations? And these are what we talk about. The stand-up time for a boulder clay is due to what we call soil suction, but it's due to low permeability. When you cut a face in the boulder clay, it will expand slightly, and because it's full of water, the water can't go anywhere, so the water becomes slightly negative and holds it all together. So the stand-up time is related to water pressure, and it's related to permeability. So if the permeability is too great, it'll all fall down. Like if you excavate a face in gravel, it'll all just collapse in on you. And the reason the boulder clay doesn't is because of the the fines, there's enough clay and silt particles to block up all the voids between the gravel to make it very low permeability. So what happens if the permeability, if there aren't enough silt and clay, then you'll find that it won't stand up long enough. It may stand up for an hour, 2 hours, then it collapses. And so that's what you need to look at. I've come across several cases where the contractor is claiming, because the thing is called boulder clay, and yet all the sides collapse. And the reason they all collapse is that it is sort of in generic term boulder clay, but the fines content of it wasn't enough to hold the suctions long enough. So, and these can appear soft in trial, but stand-up time very dependent on amount of fines, very difficult to test to get undisturbed samples, and fines content of between 20 and 30% particularly difficult, because if it's less than 20% it's going to collapse anyway, it's nearly a gravel. But if it's between 20 and 30, it can be difficult to identify it on site. And much of design based on engineering judgment and experience in that. Now I'm just going to briefly bore you with some of the finer points of geotechnical engineering, and this is really just to give you an idea of where geotechnics can go if you want to go there, if you need it. And it's really for information. I'm not going to go into the techniques, but research has contributed to confirming very stiff field behaviour. I'm talking about the black boulder clay here. And a lot of work has been gone into looking at the behaviour of black boulder clay because to see if we can predict how long it'll stand and what are the deformations will happen if we excavate anywhere near it. And so we do small strain lab, and we do field, when I do field, MASW is geophysics, and we develop sophisticated soil models. So we have developed these elastoplastic soil models based on laboratory tests and on field measurements of what we call small strain, because it's highly non-linear. Soils are very stiff at very small strains, and then they degrade at higher strains. So we do these, and then we obviously do lab tests and field tests and what we call bender elements. So a lot of the work has been trying to capture the very high stiffnesses at small strains and then to take it on into the large strain area. And to use that, then obviously we can input these soil models into sophisticated finite elements. But finite elements, as in structures, is routine. Finite elements is probably more routine now in geotechnics than it is in structures, because we would use Plaxis, and it's a very straightforward program, as Breffney knows up there, as an expert in the art of Plaxis. We had the pleasure of Breffney there for a few years with AJL. So to show you where we went, where we're going with that, this is a work that was done in Trinity with me, Pat Tracy. So we would, this was on the northern motorway, we'd excavate a face, we'd instrument the top of the slope for horizontal and vertical strains, and then we would measure the predictions, we would compare the actual measurements with predictions. Now, we put a lot of effort into developing a model and identifying the small strain stiffness, but I won't go into detail, but we were getting closer to it, but we were still not getting, that one's okay, but those predictions there, sometimes there was the measurements, there's the measurements, there's the predictions. We hadn't perfected the art, and that was in using very stiff materials, the material property, at the small strains. Then it's okay when you get the larger strains and the footing, the sort of strains you get under footing, we can get that all right, because the strains there are larger in the area that it works in. Now, I want to go back to this trial excavation and show you something that I think is important if you're going to look at temporary slopes in boulder clay. As I say, they were hoping to get away, well, get away is probably the wrong term, because they did a lot of research. These are battered back at 70 degrees. And you can imagine the saving that they would have made in construction if they could have just done the whole kilometre, battering back the slopes like that at 70 degrees without any strengthening of the slopes. But, sorry, I'm going to say this is showing off, I think, more, this is more of my finite elements, and to say that this is showing, in that slope is more of the measurements that were taken. These are predictions. And, sorry, there's the measurements, the blue. The predictions that you get, we're getting better at it. But if you use just linear elastic deformations, that's the sort of thing. If you use a simple model, you would predict those sort of movements. And yet, there wasn't measured. And strength. Okay, anyway, that's back on. Now, this is what I want to show you. So I said which is probably more relevant to you, is if you know this, it may be of help to you in your career, is that something that stands up, and it can stand up a couple of weeks, some parts of it can stand up years, but other parts can collapse. So that collapsed at 1 to 1.5 months. So, and the reason it collapsed, that there was a very thin sand layer in there. And when they collapsed, it became obvious that there was a sand layer, and that broke, the sand layer then broke the soil suctions in that layer, and the whole thing collapsed. And those finite element things I showed you before were carried out, including the effects of that sand layer, which you could model. So the point is that something stands up today, it won't necessarily do it in months or 2 months, because you're always under pressure. We get under pressure to go out and look at these slopes now, and there are big health and safety issues. You can get away for a short time if you have a lot of observational approaches in there and you're sure that everyone is aware of what they're doing, but don't expect it to stay up for very long. Okay, the next thing I'm going to go through is some of the findings of the studies carried out, not by me, but by really Mike Long and his colleagues, on studying the effects of performance of retaining walls in Dublin. And I just went through these, preparing this paper just gave me, or made me actually just look at these things in a bit more detail to see what we can learn from them. A lot of the retaining walls were done for deep basements. And as a routine now, sort of a quality control, people shove a tube into these retaining walls and they put an inclinometer in there. So people measure the deformation of the lateral deformation of the retaining wall over time. There are more sophisticated studies that are done that measure the vertical settlements and so on. And there are studies that look at the deformations, the installation effects, because like one thing from the deformation of the retaining wall itself under the loads when you have it in, but by putting the retaining wall in, you can cause, and you do cause movements. So I've listed the various papers and publications of this group, mainly headed by Mike Long. The first one is a database he was in one of the cost groups, and he had access to, I think, 169 or something like that data. They studied as a cost group, and then he took that knowledge and he looked at the deformations around Dublin. So just they obviously, what they look for is H is actually the excavated depth. There are various other things that we look at, but I'm just going to do a general overview and see what we get from the findings of his study. There's DH max is the maximum horizontal wall movement. There's DV max, which is maximum vertical wall movement, which as it happens I'm not going to talk about. And S is the average spacing of supports. But reason why I put in the average spacing of support, but what will come in is the system stiffness, which we call EI over gamma W S to the fourth, where S is the spacing between the supports. And the spacing is taken as 1.5H for cantilever. So what the study then can look at to see what the measurements tell us about how the walls performed. And I was sort of interested in is, first of all, is there any difference between a contiguous pile, secant pile, diaphragm, soldier, king post system or sheet pile wall? Now, most of the data that they've got really are concrete secant walls and so on. I'll go into the first series. The first area they looked at was retaining walls in Dublin, boulder clay. And that just gives you an idea of, he looked at a 6 metre deep excavation in Leinster House, Doyle Éireann. He looked at a 7.5D excavation for an anchored wall in Trinity, and he had a 7 metre cantilever wall in Ballycullen Road, and he had a 17.5 excavation with diaphragm wall as part of the Dublin Port Tunnel. This is a sort of way that he presents the data, or well, not he, his colleagues and whatever, they present the data. And basically what you get from it, really, there are two lines. If you look at there's a Syria report 2003, which has since been updated as 2015, I think, the Syria report now. So but it says that what you can expect is your lateral deformation about 0.4%. But the findings in the boulder clay in Dublin, I suppose not surprising, is that it's less than 0.18%. So if you have a 10 metre wall, it's not going to deflect more than 18 millimetres. Prop wall, there's a tendency for the lateral deformation to increase with height, but I wouldn't say it's really, because you've got your chart, that is your plan. So with the depth of excavation, with age, I suppose there is a tendency, but I wouldn't say it's huge. And the authors don't say it's huge. It's all performed stiffer than the world average. I'm not surprised, because we know boulder clay is stiffer, and they appear independent of stiffness. So whether you use a king post system or whether you use a secant, it doesn't really make much difference in the lateral deflections. And the vertical deflections that occur due to wall movement will usually be less than the lateral. I was interested in the cantilever wall, and there the deflections are a bit larger, and they're quite small where there's stiff soil at dredge level, at the base level, but where you've got soft at the dredge level, you can it can come up to values. Now, there are 2 points that should be made here. First of all, if you're dealing with a black boulder clay, as I said, it's low permeability, or boulder clays, and you will get the water pressures changing with time. So when you do your initial design, you'll be doing it on an undrained analysis, on undrained strength, which we know is 450, 500. And if you do that calculation, you'll find you have no pressures on the wall. So what they do then is use your effective stress, because it's unsafe. You don't know how long it lasts. And so there is this whole question of, if you're going to design your wall, before you put your props in, or is it going to be undrained or drained, or can you take benefit of the undrained in some way? So that comes on to these cantilever walls here, where the deformations are greater. But there was only one, what I call a true cantilever wall, Ballycullen, and they were looking at where they were able to look at the cantilever wall over a longer period of time, because a lot of the other cantilevers wall was just a cantilever stage in a big secant wall, and that is, it's not really the same as a cantilever wall, just designed for cantilevering. But Ballycullen was, and you want to know how it deformed in time, because soils are all related to water pressure. And they found that on that job anyway, while it did increase with time, it sort of stabilised and was behaving quite well. Then they look at glacial fluvial gravels. You can see the sort of site, that's the sort of thing in Dublin Central and all the rest. And you can see the type of the normalised wall movements appear to decrease with increases in system stiffness for that. And but they were still relatively small, so you can see the various relationships that they have there, less than 0.2%, 0.18%. So and they took a greater. And then they looked at the estuarine deposits. Now these are near the Port Clay, and there's the chart similar to before, but what they concluded from this, for the estuarine deposits, that they said that behaviour of the walls fell into two groups. If there were stiff soils at excavation level and high system stiffness, the wall movements were very small and were similar, not dissimilar to Dublin boulder clay. If there was soft at excavation level or low stiffness, then the wall movements increased. And I suppose that's fairly logical. The general comments of the authors, which is interesting, but this comes out from a lot of the measurements that have been made, is that there seems to be scope for more efficient design and construction of walls. In other words, they're made too stiff. They're made stiffer than they need be. Now, that's just a question. That may be fair enough. It's a question of what is the alternative. And in a lot of these data that you have all the walls that behaved well. What you really need is the walls to fill down and to balance it, to get the complete knowledge. And then there seems to be more scope to use cantilever wall. And I think that because cantilever will have huge economic benefits, obviously, when you're developing a building, because you don't have to get anchors in under someone else's land. You can go right up to the boundary, and or else you don't have to proper go top down or something like that. Okay, still I'll go through now just some comments on piles. I'll just give you an idea of what the experience that we have of piling in the soils of Dublin. First of all, it's not usual to get instrumented driven piles because they're more difficult. I did it when Croke Park was being constructed, the student Mike Luby, who's Bern Luby and partner, he was my student there at that time in Trinity, and we were doing it. But the interesting thing is, we drove a steel pile, and where there was that link film they were instruments, so we could measure what was going on in the ground. So we drove the pile into the ground, and what you may find interesting, if you just look at probe one there is that probe there. Look at the water pressure. We drove it, and then we measured the water pressure. And the water pressure in the pores at that time was 800 kPa, about 750, something like that. That's a fair old pressure. And that was measured at that part of the toe. And obviously, as you go down at there and there, the pressure was less. But this is time, and you see that the water pressure dropped off, and then after whatever is a week or something else, it had died off. So what's interesting then is to look. We did a test on the pile after I think it was 1 hour, and we did it the next day, and then we did it the next day, and you can see that not surprisingly, the capacity of the pile increased, and increased significantly over the time. So if you go, there is benefit in these soils of waiting, standing on, give the ground time to let the water pressures dissipate, and you'll get a stronger pile, and it's only common sense. There's a lot more information on CFA piles and board piles, because you can just put the strain gauges onto the cage and you can interpret. That's the sort of strength you get. I just want you to know 1, 2, 3, up to 4. That's the sort of shear stress that's mobilized in the pile. These are different loading conditions. And you see the CFA pile, that it's all taken, a lot of it in shaft resistance. There ain't much, it all dies off at the toe. And this is what you probably would expect for CFA pile. That's the end bearing, and that's the total capacity. So not surprising, most of the capacity you've taken on shaft resistance. Comparing the shaft shear stress distribution for the driven pile, you see the driven pile, there's a pile cap. That's the distribution of shear stress, and that's the distribution we've seen before on a CFA pile. So it's all concentrated at the toe. When I was making up these slides, I found it interesting. The sort of stress it maxes out at about 400 kPa, 3 to 400 kPa. Now, I also took out, there's a paper by Mankiti, Long and Milligan and Higgins that was done on the Port Tunnel, where they were looking at the soil nails. They were using soil nails to support the slope, because I told you, as I said before, the slopes collapsed after 1.5 months or something like that. So the only way they could build it was to nail the slopes, stabilise the slope with soil nails. And they did a lot of tests in that regard. And interesting, this is the skin friction factors that they quote. And we're up here again, 300 to 400 kPa. They get some more, but a lot of them in that area. And so it seems to be a lot of the methods are coming up with those sort of values, and they're very high shear strengths. If you look at, I don't know, you look at Thomas and all the rest, they say you should never take more than 100 kPa, something like that. Okay, now again, just to say, if you have in piles, there's end bearing. When you're looking at the end bearing piles, it's usually Cu times Nc times the area of the pile. So it's interesting to look at the Nc value that you get for different piles. And from the test that we carried out for the driven pile, you get huge values of NC. And then for the board piles, it's down to around 9 or 10, 9 kPa, 9 times, and Cu is usually about 9 for board piles. Okay, just a quick thing. Most instrument pile test results in very stiff boulder clay. Care must be taken when using the findings of driven piles in boulder clay to another boulder to outside Dublin. And I just a health warning really, just to be careful of using the techniques we do here if you're going out into other areas of Ireland, because I've called in on several times when things have gone wrong because people have tried to extrapolate experience in very hard boulder clay into boulder clays which aren't the same. I just run through some sort of tests that we had carried out in the different rocks, because rock socket is a big thing if you're doing any major construction in a major development in Dublin, any of the structural developments. So that there's a lot of pile tests. This was done in Dublin Central, and we were able to instrument the pile so we can load it up there into, I think it was kilonewtons, 18,000 kilonewtons, and it was a 2.5 meter rock socket, and it was basically to see, because the rock was coming up with poor quality, poor strength qualities, and so we wanted to see if we could get the strength that we needed. And this and many of the other projects we were doing in association with T.G. O'Connor, so I would like to acknowledge their permission in giving this information. So diameter rock socket is 1.06, and it was about 2.5 meters. And you see, we can relate. You can see where in the different these you can see the stiff layers that we were concerned about, and but in there, because the force there, we were, although it was firm to stiff clay, we were getting a lot of shear stress taken there, and curious enough we weren't there. So these things gives us information. Now, just before I go into that, I put this as an aid memoir, the findings of piles in Calp, rafting. Because one of the things that showed up very clearly when they were doing the Dublin Port Tunnel, because they were able to excavate, they did excavate faces, particularly for some of the shafts, down onto rock. So you could sometimes see the boundary between, say, the boulder clay and the rock. Now, I'll show you a photograph later on but of the Calp limestone. But you can imagine the ice is coming along. As we say, we grind up. The lodgement tail is a ground up rock at the base of the ice. But sometimes the rock moves with the ice sheet. So you get what we call a raft of rock. And the raft of rock can be hundreds of meters going with the ice. And then underneath the rock, you can get some clay again. And then the true rock head is at a lower level. And there was an example of that in some of the excavations. So when you sometimes you may think you're on rock and you're not on rock. And it's purely just it's unusual, but it does happen. Anyway, I won't, in the interest of time, you've got the notes on this, but basically this test enabled us to design piles in the weathered limestone rock, which had basically, as I said there, RQD 0 to 8% generally, which means that it comes up nearly as a gravel. And we had to show that it had the capacity, and you could get piles to design piles for the load, for the very, very big loads that were required on that project. Unfortunately, the Celtic Tiger collapse took its toll on that. Okay. Just to show in that, this is just more details. It was done with one of the bower rigs, so they have a core barrel at the end of it. And that shaft that we were looking at, we did a smooth core barrel, so we had a smooth shaft. We didn't want, we didn't put a rotary bit on it, so we'd have a rough case. The worst case would be smooth, and you can see some of the rock coming up there. It's not the best. We also, again with Teacher O'Connor's, we looked at Dundrum shopping centre. This was the extension. We were involved in the one that's up there now, but also in the extension that was proposed, and that was going to go down to the bowels of the earth. But the thing about granite, it weathers in what they call foliations. It weathers like an onion. The thing pops up off it. But where you have fissures in it, it weathers along the fissures, and it weathers to a sand. So you get hard rock, and then you have zones where it's back down to sand. And the question is, how do we handle that? And this is, we obviously pile test. That was just a novelty. They put on a pressure cushion at the base of one of the pile to measure the toe stress, but I don't think it was very successful. So the sort of mobilised stress we mobilised. We didn't fail the pile. But you can see that all the load was coming on in the socketed area down here. So we're mobilising about 820, which was very good for the weak rock we had. But in some of the piles, the mobilisation wasn't uniform. You can see that it was some of the layers were taking, there were some hard areas within the granite that were taking up most of the load. So again, the pile, there were several piles in granite. They were 900 to over a metre, socket lengths of various lengths, and applied load up to 18,000 kilonewtons and settlements. They all performed well. Now, what is more interesting in this job, that this is the Dundrum Shopping Centre. At that time, there were basements going down 20 metres. So it was a big job, and they were doing a secant wall right around it. They went to tender on the secant wall and the piles, and the prices came in, and they were astronomical. There was a lot of piles, a lot of work. These test results, and also we did constructability tests. We looked at piles and looked at the rate of constructing piles, because they had to go down through granite, and the granite, some area was strong, very strong, and then weak, and so on. And when they re-tendered it, it came in 30% cheaper than the first, because of the information they got from these trials. And it was a big contract, you know. So it made the whole thing feasible, having these trials. Okay, now I'm just going to talk about the Dublin Port Tunnel. You have the Dublin Port Tunnel, Port Clay. This is very interesting geotechnically, because, as I say, it fills the area, all this area around Ringsend, and also this area here is to Alexander Quay. We were designed that, and we had to do extensive finite element 2 and 3 dimension finite element analysis on the quay to come up with the design. Just a brief, I was involved with P.H. McCarthy when he was doing the Ringsend, the original Ringsend. What you get is made ground, you get fill, then you get estuarine sands, and then you get this port clay, which is kind of 15 or 20. But the port clay is down at about, depends, minus 15 metres OD, something like that. It's not near the surface. It's below sands and gravels and estuarine material. And when it goes down to a great depth. When the ESB were doing the initial power station, I presume it's Ringsend Power Station, they called in some of the big honchos in geotechnics from England, and they said the port clay was soft, and so Ringsend Power Station, the piles went down 60 metres, and there were 2 metre diameter piles going down 60 metres, and they had huge problems putting them in. Needless to say, they had to use what's called a Benoter piling rig. So after that, I was involved in several projects, and I said, it ain't soft. And that's where the big thing is. Now, these are properties. I only show you these to show you the trend. It's fairly uniform. These are sort of what we call liquid and plastic. These are indices we use to look at the nature of the soil. It's it's not what we call highly plastic. It's there's a scattered uniform, no plasticity. If you look at the SBT values all over the place, and then there was a lot of development going on, so we had to do this. Now, this is, again, if you take samples, take your U100s, take whatever you call it, and you test it, you find that you come up with underrange shear strengths. You see these underrange shear strengths about 60 kPa, 70 kPa, and that means that a lot of when you analyse it, a lot of the old works around the rings, along the quays, should have fallen in a long time ago. So there's a lot of effort was put in, and David Gill from our office summarised it there in a paper recently, and it's on the Engineers Ireland website. But if you take your samples and stress them, put the stresses back that they had in the ground before you took them, you find that the strengthened material is much greater than what you do if you test it initially. And if you do CPT, you see these are what we call CPT, these are strengths that are inferred from in situ tests. So you see, rather than to have it down here, the strengths here now are 120 kPa. So you've got a 50% increase in strength, if not more, when you do these tests properly. And that ties in with good quality lab tests. And it enables a lot of the developments in Ringsend to go ahead because it cuts the cost. And we have also what we call strength parameters and so on. But the point I'm making here is, and this is a good illustration, that what you do now, this port clay isn't as soft and isn't as weak as they thought before, it's stiffer. So what you do, what we've done now is that you pile everything. There are sort of pockets of silt and clay, but you form everything on piles that achieve their end bearing in this pile here. You've only got about 3 or 4 meters because you've got soft soils up here and you've got there. But you have to put your piles in the gravel, but the piles have to be a sufficient height above the port clay so you don't overstress it. And then everything works. So on that basis, as you see, the SCR tanks and everything that I showed you before were constructed in port, and the turbine bases for all the follow-on turbine for Poolbeg station, they were all founded on piles that were in the upper gravels, because once you go into port clay, it's stiffer and everything else, but you won't get an end bearing of a pile in it. If you reach the port clay you have to go straight down to the rock, which is about 40 meters below. Okay, so that's an overview of looking back on the experience that we have gained over the last few years. Hopefully you've learned something about the important geotechnical features that are on in Dublin: the preglacial valley, the major fault, our boulder clays, the port clay and the pyritic rock. It can be difficult to determine properties of boulder clays, but we've got good experience of it. Hopefully you get from it the percentage fines of the boulder clay have an important impact on the stand-up time and other factors. There's significant research both in lab and the field into the behaviour of black boulder clay, so we can do sophisticated analysis if we have to, and we do it in cases where you're building closest to big structures. We're doing it in other areas of Dublin where there are sensitive structures nearby. and we would do the fancy work on that, and it's very readily. There are good case histories of retaining wall performance in Dublin plays by Dr. Long and his colleagues. There are significant differences in the way a driven and CFA pile perform. We have case histories of pile sockets in limestone and granite rock, and I find from major projects such high quality testing has commercial benefits on the project itself. And the additional strength and stiffness of formation of portal clay is in line with that indicated in the paper I gave in 1990, but it was more unique at that stage, so taken now. So that's it. So I hope you got some knowledge out of it. Thank you.
I think I'll dust off my old 1990 paper now. It's been terrific that. Things have moved on a lot, and there's a lot of, I've just seen the names of Michael Long and Michael Luby appearing quite a lot in that.
Yeah.
A lot of research. Have we any questions?
Yes?
Thanks for the talk, it's very good. Just intrigued by the trial excavation of it in Dublin Port that was done. So there's two questions. First, the sand layer was the cause of failure. Could have there been some modelling to identify, that was going to fail? I presume it was a sort of instant failure. And then secondly, you touched on the observational method, which obviously is an important part of AN 927. Other than soil nails, were there other interventions that could have been possible with using the observational method had the team decided to do that, such as shotcreting or something like that?
Okay, the first part of the question is, could they have predicted? They had instrumentation in the ground, and it was clear that the movements were associated with the sand layer. So it was clear from the movements of the inclinometers that certain areas were going to go. Just it was a question of time. The observational approach, the way it was, the observational approach was used, and they did so. What they did was they soil nailed a certain amount of it, and then they left the rest of it based on observations. I was checking it for Dublin County Council guide on that thing, and one thing the analysis was great and all the rest, but what I've always said with the observational approach, I said if you're going to use it, you have to have a remediation measure in place real time. So they have to have, the remediation measure usually in case like that is put a berm up there. So you have to have mirrored. And curiously enough, they came on an area near one of the bridges where the ground was particularly bad, and the movements were larger than they expected, and they did have to use remediation measure.
How close was that house?
There wasn't a house.
To the house that we saw in the photograph, there's a house perched up.
Oh, I can't remember it now at that stage. A good bit away.
More than 11 meters.
Ah, right, yeah. No, it's not right.
Thanks.
Any other questions?
Talk about testing ideal savings on one project, but my curiosity is that the Irish National Annex don't allow for adoption of factors of safety for testing when the UK National Annex does. Just wondering why, or you think that the Irish National Annex should do that for pilot?
The Irish does allow you to reduce it with testing.
Does it?
Does, yeah, definitely. And a lot of these, big time.
The partial factors.
Yes, yeah. Well, it does the other way around. If you don't do testing, you have to multiply them by a factor of 3. Whatever it is, in other words, not 3, I think it's 2. There's big time in the Irish National Annex, probably more. The UK have a different way of testing, and I know you're talking about the proof testing and so on that the UK National Annex has. But we do have the partial factors are reduced if you do pile tests, as reduced depending on the number of pile tests you carry out. I know the UK have a system which is to do with I suppose the Irish one would be on the preliminary pile test. The UK allows you to benefit from the proof tests that are carried out during the project. We just haven't put that in. It's something that we will look at, and it's on, like I'm chairing the panel on the Euro code, and it's something that is on our to-do list, is to look and reassess our factors of safety or partial factors for pilot design. But it would only be like the two things that are important is not only the proof testing, are they is significant, you only take them up to a certain value. Does that give you enough safety margin? And then there's also the CAP-RAP and all the other tests that are coming in. Are they any use? And we've done a bit of work, but we need to do a bit more work on it, because the dynamic tests are used now, and it's how to use the dynamic test more than anything else. But they can be incorporated. It's all a question of trying to make sure that you've got a safe product. Really. But Irish National Line does let you benefit from
it's just not the
that.
same reduction as maybe, working pile and preliminary test.
It doesn't. Yes, they're all on preliminary tests, not on the working piles. Yeah.